Namaskar to everyone and good evening. Today is the 101st birth anniversary of Professor Baidyanath Misra. And Professor Baidyanath Misra was the founder secretary of the Orissa Economics Association. And in fact, he attended almost all the conferences starting from 1968 to 2018. That was still the Golden Jubilee Conference. And he edited the Orissa Economic Journal almost for more than 30 years. It would be probably 30 years he edited the Orissa Economic Journal. Because initially there were other members who used to edit the journal, but then Professor Baidyanath Misra edited the journal for almost four decades. And so that's how he has, you can say that, brought this association to the Golden Jubilee years. And he was so committed to the association. And
sorry, Amarendra, but I think there's some disturbance. Maybe you should request everyone to mute. You see, there's some disturbance.
Yes. So, Lakshmikant, please take note of that and please mute wherever the noise is coming. So I was telling that Professor Baidyanath Misra was so important for the association, and he just passed away in 2009, just after Fani cyclone. And in fact, that was so sad here that even the formal events like, say, bringing out say souvenir or anything, that could not happen because of that Fani cyclone and all that. But anyway, the Orissa Economic Association has been organizing this endowment lecture, and the corpus fund was donated by his son, Dr. Vasant Misra, who is a neurosurgeon at Hinduja Hospital. I think family members of Professor Baidyanath Misra will be also joining with us. In fact, today I will be, basically, since I have some other important work, and I'm not in my office, I'm outside, so that's why I have joined from my mobile phone. Okay, so I will be basically requesting Professor Kesav Das, who is the executive editor of the Orissa Economic Journal, and also I can inform you officially that the executive committee has also nominated him as the president for the next year. So he's president-elect, you can say. Of course, I'm announcing it a little in advance. So he will be the president for the year 2023. So he would be basically moderating the session. But before that, I welcome the star of this evening, Professor Debasis Misra, who is currently working at Indian Statistical Institute. And more information about Professor Misra will be given by Professor Kesav Das. And I now invite the president of Orissa Economic Association, Professor Sujanarayan Tripathi, to preside over the meeting. And following up, it will be followed by basically after that, Professor Kesav Das will be basically taking over the session. So it's over to you, sir, Professor Sujanarayan Tripathi, the president of Orissa Economic Association.
Good evening to you all. Namaste. In fact, I am very much delighted to be present here to welcome Professor Debasis Misra as the speaker of Baidyanath Misra, Professor Baidyanath Misra's memorial lecture. And I also welcome all of you to this August gathering. Today is November 22nd, the 101st birth anniversary of late Professor Baidyanath Misra, an eminent economist par excellence, a renowned personality, a great administrator, able administrator and educationist, and was a vice chancellor of Orissa University of Agriculture and Technology, founder, director and chairman of Nabakista Center for Development Studies. He was also the founder of Orissa Economic Association. He did his commendable service for Orissa Economic Organization by conducting annual conferences every year till he breathed his last. And also he brought out regularly Orissa Economic journals. He had made a dedicated service for the cause of the institutes and poor people also, organized several camps. So such a great person he was, and we remember him today in his birth anniversary. And we have our esteemed speaker who will give an address as a tribute to Professor Baidyanath Misra. Uh, Professor Debasis Misra is a professor in the Economics and Planning Unit of Indian Statistical Institute, Delhi, and is very renowned person also. We know, all of us know him, and we will find more interest in his research-based, thought-provoking address. I welcome all of you. I express my thanks to all of you for your gracious presence. Now I request Professor Keshav Das, Gujarat Institute of Development Research, Ahmedabad, to act as a moderator and to see that this memorial lecture should continue most perfectly under his dynamic stewardship. Now, hand over to Professor Keshav Das. Thank you.
Thank you very much, Professor Tripathi. I think you have really already introduced the significance of this specific evening today. And this is the 101st birth anniversary of the very, very, if I may say that, it's a kind of the most enduring economist of the state of Odisha, whether he's physically with us or not. So for us, it's a very, very significant event. And just to think of Professor Baidyanath Misra, because he has, as Amarendra pointed out, he has been with us for such a long time, and I think he played a kind of varied role. I mean, he was not just a teacher or an administrator. I think he was a very deep thinker. I mean, and he was, to me, looks like he was one of those very rare economists who actually communicated with people. Actually, in fact, he had been continuously writing columns in the newspapers. He has written in Odia. He has communicated with students, with ordinary people, and of course, he was very much at the helm of affairs when the policy making was concerned. So he was someone, I think, extremely unique personality for us, very inspiring for the generations. And he also put in so much of hard work, as Amarendra said, for the Odisha Economics Association. In fact, I'm not very sure if many of you would have seen his autobiography called The Pursuit of Destiny, published in 2013. So if you go through that, I mean, that's the Odia version of that. If you go through that, you actually sort of make out what all hardships in the initial days he had gone through, from absolute adversity that affected his own personal life. So I think he felt for the people, and that was very much sort of part of his own personality, his own life experiences. So in that sense, I think apart from his sort of several books that he has been writing at least since the 1970s, whether on public finance, whether on agriculture, whether on education, whether on public administration, so varieties of books he has written. He had been communicating with the younger people, and it is with that that I'm personally very happy, and on behalf of the Odisha Economic Association, I'm very happy to welcome Professor Debasis Misra, who also has today chosen to introduce us or to sort of let us, particular to the younger scholars, I would feel like he would be sort of introducing us to a relatively less known area for us, that is on market design. He would be talking to us about that in great detail. And very, very briefly, if I may introduce him, let me start by saying that he's an extremely nice, very polite, very humble person. So I think that makes him a great human being. But apart from that, he's also the professor of at the Indian Statistical Institute for quite some time now, and he did his both PhD and MS in industrial engineering from the University of Wisconsin in the US. He also did his graduation at IIT Kharagpur. And what really impressed me very much from his profile is that he has been sort of publishing in some of the top journals in the field, whether it is Journal of Economic Theory, Theoretical Economics, Journal of Mathematical Economics, Games and Economic Behavior, Social Choice and Welfare, Econometrica, Journal of Mathematical Economics, and a number of other journals which are more in the domain of engineering. So it's very rare to find someone with a very strong engineering background, but then talking to us about economic theory. And he has been professionally recognized through a Social Choice and Welfare Prize in 2018. He also received the very coveted Mahalanobis Memorial Medal in 2016. And he has been a council member of the Society for Social Choice and Welfare since 2016. So with that very limited introduction, let's listen to Professor Debasis Misra. And as he suggested, and as we think it might be in the fitness of things, that he would prefer questions as he proceeds. But before I make that request, can I just make a very small request to Dr. Basant Misra, the eldest son of Professor Baidyanath Misra, if he would like to say a few words, because it is in honor of his father, but then he's also he's very much with us as an economist. So Dr. Basant Misra, if you'd like to say just a few words before we go to the main talk.
Thank you very much. I really appreciate it. Thank you very much for doing this. We are grateful to you. My family is very grateful to you. I'm actually not economist. My brother is economist. I think he's there. Sukant Misra is there. It's appropriate that he talks about it because I'm actually a doctor. I'm a neurosurgeon. I'm not economist. But my brother, Sukant Misra, who is in Texas, I think it's better he talks about a little bit about my father. He's my youngest brother. He's online now. So I pass it on to Sukant. Yeah. Go ahead, Sukant, please.
Yeah, please.
Good morning. It's an honor to be among you when you talk about my father and then introduce a topic in economics, which is extremely important nowadays. So I look forward to listening to the presentation. As my brother said, I'm Sukant Misra. I'm the youngest son of Dr. Baidyanath Misra. I am an economist. I'm actually is an agricultural economist, just like my father was. And he inspired me to pursue the field of economics. He inspired me to come to the US after I completed my master's in agricultural economics from Bani Vihar. I came here and completed my second master's in agriculture and applied economics and a PhD in the same subject. Then I'm working with Texas Tech University right now as a professor of agriculture and applied economics, and also as the vice provost, which is the same thing as vice president for international affairs. So this meeting is not about me. This is, of course, about my father and all of you, as he has inspired a lot of you who are in front of the camera today. He has inspired our entire family, regardless of what we are doing today. We really appreciate your time, effort, and interest in his life and his contribution to the field of economics. Thank you very much.
Thank you, Professor Sukant Misra. It was very nice of you to have spoken to us. And now we come back to the main part of the event. And Professor Debasis Misra The floor is yours. Yeah, thank you very much.
Thank you very much. Thank you. I just wanted to check if I'm audible. Okay.
Yes, sir, you are audible. Yeah.
Okay, thank you. I was so happy to learn about Professor Baidyanath Misra, who was not only a great scholar, a great agricultural economist, but basically a very important institution builder in Odisha. I don't think I know anyone who has done for institution building in Odisha than Professor Baidyanath Misra. So it's a great honor to give this lecture today. And thank you, Odisha Economic Association, for arranging this lecture. I'm also very happy to join the list of speakers who have spoken before me. So I'm really honored to be on this list. So without further ado, I will start today's lecture. So just for the logistics, I will take questions as I go along. So can you all share, see my screen still?
Yes,
okay.
yes.
Okay, thank
yes.
you. So today's talk will be on market design. If you are not familiar with it, this talk is aimed at giving a brief overview of what this field is. My own research is somewhere at the intersection of mechanism design and game theory. It's related to market design, and as the talk progresses, you will probably get a better idea. And so it's a relatively new area of economics, both theory and experiments aspects of it. So the way to think about it is economics started as a field which tries to analyze markets, games, etc. Then it moved to designing of markets and games. And that's where the area of mechanism design came into being. Where market design is different from mechanism design is the fact that it deals with details and of practical aspects of markets in real life applications. Mechanism design, as you know, is what is called the reverse engineering of game theory. But for problems coming from real life application, we really need to get into nitty-gritties and details. And that's where market design differs from mechanism design, or separates itself from mechanism design. So here is a quote from Alvin Roth, the 2012 Nobel Prize winner. Economists have lately been called upon not only to analyze markets, but to design them. Market design involves a responsibility for detail, a need to deal with all of a market's complication, not just its principal features. Designers, therefore, cannot work only with simple conceptual models used for theoretical insights into the general working of markets. Instead, market design calls for an engineering approach. So this is part of a lecture that Al Roth gave in the Econometric Society meetings. And this is from where essentially the term economist as an engineer, or the phrase economist as an engineer, became very popular in economics. So he's calling for economists to work more like engineers, which is to my liking because my background is in engineering. And so today I'll convince you that the area of market design is closer to engineering than to perhaps economics. Okay, so of course I am a theorist, so I work on micro theory. So some of the things I will describe will have a theory undertone, if you will. But really the area of market design has a lot of experiment, has a lot of data, and has a lot of practical applications. And I'll try to touch on some of those aspects also. One of the features of market design is that it covers multiple disciplines. So I already said that economic theory and experimental economics, in economic subfield, they are the active areas which work on market design. But also it borrows ideas from operations research and computer science. Okay, so it's really an interdisciplinary field, so to say. And two applications that essentially, brought this area to prominence. One is an application in matching, and I was happy that one of Professor Misra's son is a neurosurgeon, and he might be able to relate to this. So Al Roth was the first one to think about ideas from matching theory to be implemented in National Residence Matching Program in US. So the National Residence Matching Program in US involves matching doctoral students for internships for different medical schools. So they used to follow a particular kind of allocations of these interns to medical schools. Al Roth was the first one to systematically think about how this matching should be done. And he applied these ideas from matching theory to actually come up with a better matching algorithms for matching these interns to various hospitals in the US. Later on, he also applied these ideas to various school choice problems. And all this application work led to a Nobel Prize in 2012 to Al Roth and Lloyd Shapley. I'll talk about another key contributor to this field, David Gale, who had passed away by 2012. But if he was alive, I'm sure he would have also shared the Nobel Prize for this. The other kind of a parallel stream to matching, which is also equally relevant in today's day and age, is auctions. In particular, design of combinatorial auctions. I'm sure you must have heard about spectrum auctions that the governments organize. And in 90s or late 80s, the government of US decided to conduct what is called combinatorial auctions to assign spectrums or allocate spectrums. And that required getting into the nitty-gritties of the details of these designs, and which involved a lot of practical constraints. And Paul Milgram and his co-authors and various other people helped design the combinatorial auction markets for these kinds of auctions. And some of these ideas are still used to assign spectrums in various countries. And so Paul Milgram's theoretical as well as practical work, as well as some of the earlier contributions are due to Robert Wilson, led to a Nobel Prize in 2020. And in today's talk, I'm not going to spend time on auctions, but I'll mostly focus on matching, mainly because the ideas in matching are very easy to convey and still very relevant. And so most of the talk will be on matching. So those of you who may have heard me give a talk on Nobel Prize lecture earlier in the same forum may recollect what that work was about. So today it's only going to be about matching markets. So before I dive into matching markets, we all know that resource allocations are usually done with the help of transfers or money. Government allocates its resources, coal mines, spectrum, airport, etc., by conducting auctions, which involves large sums of transfers. IPL sells players to teams, public goods are provided with taxes. Even you sell a house, then it involves a monetary transactions. It's very difficult to imagine markets without a procedure for price discovery and prices. And one of the main reasons is that prices help in creating incentives, right? And so these incentives are important to discovery of prices or discovery of right prices. And there are very well-known procedures like auctions or bargaining and so on to discover these prices at which markets can operate. Resource allocation without money, it's very difficult to imagine. Okay? And that's mainly because prices and market clearing are so fundamental to economics that we can't think of markets without prices. However, there are many markets which operate without transfers or prices, and resources are still allocated. And why would you think that prices or monetary transfers are not permitted in certain markets? Well, it might be due to ethical reasons. For instance, voting. Okay, so there are voting institutions and which run for centuries, and we know that typically these institutions don't allow for don't allow monetary transfers. There are also markets which do not allow monetary transfers because of legal reasons, like organ donation. Organ donation, legally, there are some countries where you can pay money to get organs, and there are countries where you can't pay money to get organs. So these are purely donations in that sense. So these are some of the applications that you should keep in mind when you think about markets without any monetary transfers. Okay, so inheritance is another procedure where you allocate some endowment which is left behind amongst the claimants, right? And so today's talk will be about matching, which is one of the important applications is basically dating markets, right? So I'll talk more about this. The other important application is college admission. So how do you assign students to colleges? You might think that colleges charge tuition fees. So isn't that prices or transfers? Well, these prices are fixed. So so we are not. There is no procedure which takes into account preferences of students and determine dynamically the prices that it should charge given these preferences. So in that sense, tuition fees might be there, but they are not sensitive to preferences of students. So in that sense, this is also another application where we are operating or designing a market without the help of prices or transfers. So as I said, so I'm going to be talking about market design for matching. It's a new area of economic theory and with a lot of empirical and experimental implications. It's going to be about how to allocate private goods without money or with money, but payments are not sensitive to preferences. And there'll be a new set of desiderata that I will talk about. So stability, envy, limited incentives, so new kinds of objectives. And we'll talk about new kinds of procedures or problems. Okay, and I'll give you a brief tour of this literature. So the basic problem that I will talk about, it's what is called a two-sided matching problem. So there will be two types of agents, and agents from one side need to be matched to agents on the other side. It will cover many examples, including some that I have already talked about, but the things like matching workers to tasks, matching men to women on dating website, matching students to universities and colleges and schools. And I'll essentially, you should keep in mind that the basic model that I will talk about, you can extend it in various directions. And there are three prominent directions with which a lot of work has been done. And I'll give you some survey articles to go through it. And the three prominent directions are school choice, which is an application in which many school districts all over the world, not only in the US, but many parts of the world, use insights from the matching theory to allocate students to schools at various levels. Okay? Second application is organ donations. So think of, in the previous slides, I said 2 types of agents. So what are the 2 types of agents in organ donation? So there are patients on one side and organ donors on the other side. And you need to match organ donors to patients. And you can use insights from matching theory, some of the things that I will discuss today, to come up with better organ donations. So sorry for the typo on the organ. And then the third application, which is becoming more and more popular these days, is on affirmative action policies. In jobs and higher education, seats are usually reserved for minority candidates, and the insights from matching theory can be used to find better methods to implement these affirmative actions. So I won't have time today to cover all these applications, but today what I plan to do is basically describe you the core model of matching theory and discuss the primary result in this area through some examples, and then tell you how you can extend it to various different applications that we just discussed. Okay. So as I said, I'm happy to take questions as I go along. So if you have any question at this point, please feel free to ask. Okay, if there is none, then I'll just go ahead. Yeah, okay, good. So, so the simple model that I will describe is that of what is called the marriage market. Although it's called the marriage market, because of the applicability of the model, I'll basically describe it in the context of student assignments to colleges. Okay, so think of 2 types of agents: students and colleges. And so there is a finite set of students, let's call them S, and a finite set of colleges, let's call them C. For simplicity, and only for simplicity, let's assume that the number of students is the same as number of colleges. And let's make one further assumption, that each college can admit at most 1 student. I think the assumption that each student can go to at most 1 college is absolutely plausible. But I'm making this restrictive assumption that each college has a quota of, has just 1 seat. Okay. Everything I'm saying can be extended to more general framework. Okay. So what is given to us, the economic content of the model is the following. Each student, let's denote it by small s, has a strict ranking over colleges. Okay, so I'll denote this by this symbol squiggle s, and each college has a strict ranking of I should say students, sorry for the typo. So each college has a strict ranking of students. Okay, so that's squiggle C. Okay, so one example is like this. So there are 3 students and 3 colleges. S1, S2, S3 are the 3 students, and C1, C2, C3 are 3 colleges. And here I have shown you one possible instance of this problem, where student S1, for instance, ranks college 1 at the top, college 2 at second, and college 3 at third. Okay. College 2, for instance, ranks student 2 at the top, student 3 at the second, and student 1 at the bottom. Okay. So the basic question, which looks pretty straightforward, is that how to match students to colleges. Okay. And of course, there are many ways to do it. I mean, there are many possible ways that you can match these students to colleges here. I think the important idea here is that you need to be sensitive to the preferences of the agents, okay? Both to the students as well as to the college's preferences. And you can impose some economic objectives. Let's say that you want to be Pareto efficient, you want to be fair, okay? So very broadly speaking, but you can come up with your own criteria and objectives and say that, well, this is a matching which satisfies X, Y, Z criteria. Okay. So in 1962, David Gale and Lloyd Shapley came up with a brilliant way of matching students to colleges. Okay, those of you who are not familiar with David Gale and Lloyd Shapley's paper, I strongly encourage you to look at it. It's called College Admissions and Stability, I think, if I'm not, I will share you the exact details, but it's published in 1962, and it's a beautiful paper in the sense that it contains no mathematical equations, and still it derives the most important result for matching theory. It is the foundation for matching theory, and so it's so beautiful that to an audience who is probably haven't heard the term market design, I think I should be able to convey what the main idea is. Okay, so Gale and Shapley said that even though there are many ways to do it, there is one kind of canonical way to do it, and it seems like this is very striking way to do it because it satisfies one compelling property, and in some way it is the only way to do it to satisfy that property. Okay, so without further ado, let me introduce the main property that they called stability. And so what is stability? So we'll say a matching is stable if there is no college student pair such that they prefer each other to their matches in the matching. Okay, so slightly notationally, if I were to say this, we'll say a matching, we'll denote a matching by mu. And when I say mu of S will denote the college assigned to student S, and mu inverse of C is the student assigned to college C. And what mathematically the object that Gale and Shapley are referring to is a matching mu, which assigns each student to a unique college. Is a matching mu is stable if there is no college student pair C and S such that S likes C to his match in mu. That is, according to the preference of student S, C is preferred to the college that it is assigned to, which is mu of S, and college C prefers S to the student it is assigned to, which is mu inverse of C. Okay, so a matching mu is stable if I cannot find such a college student pair. Okay, so if such a pair exists for a matching, then we'll call this pair a blocking pair, and the matching will be unstable. And so here is an example to concretely understand that, the same example. So here I'm showing you a particular matching where student S1 is matched to college C1, student S2 is matched to college C2, and student S3 is matched to college C3. Think for a minute, if you can find a college student pair who prefer each other to their current matching. Okay, so obviously student S1 cannot be involved in such a blocking pair because student S1 is already matched to its top college, so it cannot block. So the only two candidates are student S2 and S3. Okay, so S2 can potentially block with college 3 because it is matched to college 2, and college 3 is the only college which is ranked better than college 2. So indeed, let's consider the pair S2 and C3. And if you look at it, S2 and C3 indeed form a blocking pair because according to S2, she prefers college 3 to college 2. And college 3 prefers student 2 to student 3. Okay, so in that sense, S2 and C3 prefer each other to whatever they are matched to in the blue matching. Okay, so that's why the blue matching is not stable. So it's not a stable matching. But here is a stable matching. Okay, so this matching differs from the earlier one in the sense that S1 is matched to S2, S2 is matched to C3, and S3 is matched to C2. Why is this a stable matching? Well, the only student which can block is S3 because S1 and S2 are matched to their top colleges. And why would S3 not able to block? Because I'm claiming it's a stable matching. So S3 should not be able to block. Because if you look at C1's preference, okay, S3 is ranked right at the bottom. So C1 will never prefer to be matched with S3 than to whatever it is matched to, which is S1. What about C3? Well, C3 is matched to its top student. So it cannot be part of any blocking pair. Okay. So what it shows is that this blue matching is indeed a stable matching. Okay. So you can ask, like, why do we care about stability? I mean, why not something else? Okay, so hopefully by the end of this talk, you'll be convinced that stability is a plausible criteria to match. But if you think about it from the definition itself, what stability ensures is that the matching does not break expose. So, so as the word suggests, that if you were to propose this matching to, let's say, students in colleges, there won't be any exposed negotiation to rematch students to colleges. Okay, so in that sense, it will be stable in that sense. You can also formally show that it's stronger than Pareto efficiency. So in that sense, that every stable matching is also Pareto efficient. So if you can come up with a stable matching, it will also be a Pareto efficient matching. What I will not discuss today is the fact that stable matchings show amazingly beautiful geometrical structures, which are called lattices in math. So the set of stable matchings form what is called a lattice, and this lattice has a maximum point and a minimum point, and I'll get to some of it a little bit. So in some sense, if you were to optimize in the set of stable matchings, you should be able to find the best stable matching. And finally, there are beautiful procedures, and one of which I will discuss today, to find stable matchings. And these procedures have good incentive properties also, something that we care a lot in economics. Okay, so two questions that I will describe, an answer to in today's talk, which is also concerned which is also the topic of Gale and Shapley's paper, is that does a stable matching always exist? So is this example, like, I just cooked up this example for you so that there is a stable matching here. If you give me an example with 100 students and 100 colleges with arbitrary preferences of students and colleges, can I still find a stable matching? So that's the first question. Does a stable matching always exist? If yes, can we find an optimal stable matching? So what is the best stable matching? So suppose I'm able to tell you that a stable matching exists. So is there a best stable matching? And so that's basically the content of Gale and Shapley paper. So Gale and Shapley in the 1962 paper proposed an algorithm which basically you give any instance of this problem with how many number of students, how many number of colleges, college can admit many students, and number of students can be anything, number of colleges can be anything, and the preferences can be anything of colleges and students. The algorithm Gale and Shapley proposed will find a stable matching at any profile of preferences. So you give any profile of preferences, the algorithm will give you a stable matching. This algorithm is called the deferred acceptance algorithm. It's used in practice in many matching contexts. So it is the backbone of modern matching theory. We'll also discuss that the algorithm is optimal in some way. So the stable matching discovered by the algorithm is optimal in some way. And the Nobel Prize in Economics in 2012 was awarded or shared by Lord Shapley and Alvin Roth in 2012 because of this particular algorithm and its applications to various matching problems in practice. As I said earlier, if David Gale was alive, he would have been an equally deserving recipient of this prize, but he was not alive when this prize was awarded. Okay, so let me illustrate the algorithm through this example, and then it will be very clear how the algorithm runs. So as I said, in this example, there were 3 students and 3 colleges. And so the algorithm has 2 versions. One is student proposing and the other is college proposing. And it's an iterative algorithm, iterative procedure. And the version that I'm describing is the one where students propose. So in round 1 of the algorithm or iteration 1 of the algorithm, each student proposes to its top college. Okay, so S1 proposes to college 1, S2 proposes to college 3, and S3 proposes to college 1. Okay, so these are the top colleges of these students. So colleges get these proposals, so these are highlighted in red. So college 1 gets 2 proposals from student S1 and S3. College 2 does not receive any proposal in this round. And college 3 receives proposal from only 1 student, which is student 2. Okay. Next, colleges tentatively, so the word tentative is very important, tentatively accept the top proposal that they receive. So for instance, college 1 received 2 proposals from student S1 and S3. It tentatively accepts students 1 and rejects student 3. Okay. College 3 just received 1 proposal, which is from student 2, and it tentatively accepts student 2. So this completes round 1. Then we go to round 2. So what happens in round 2 is that whichever student got rejected in round 1 proposes to its next ranked college. Okay, so student 3 got rejected. So its next ranked college is C3. So it proposes to C3. Okay. So in this round, college 1 has only 1 proposal, which is S1. And college 3 now has 2 proposals, S2 and S3. So these are the tentative assignments from the last round. So college 3 takes a fresh look at this round's proposals, which is from S2 and S3, and it chooses the best one. So in this case, it so happens that the previous round's tentative assignment or the student that it accepted continues to be its top choice also in this round. This need not be the case. It could be that S3 is ranked higher than S2. In that case, the tentatively accepted student S2 would be rejected and S3 would be the tentative assignment. But in this case, in this example, S2 continues to be the top student of college 3. So it continues to maintain the same tentative assignment and rejects S3 again. Okay. So S3 is rejected again. So it now has to go to its next ranked college, which is C2. So in this round, S3 proposes to C2 again, and in this round, every college has exactly 1 proposal, and that is immediately accepted. Okay. So at the end of this round, because each student has been tentatively accepted in some college, the algorithm stops. Okay. And this is the final assignment of colleges to students. So college 1 gets S1, college 2 gets S3, and college 3 gets S2. Okay. So since there is no more rejections in this round, the algorithm stops with the output S1 assigned to C1, S2 assigned to C3, and S3 assigned to C2. So this is the this is the matching that I initially talked about, and I showed you that it is stable. And more generally, the steps of the DAA is deferred acceptance algorithm is exactly that. Initially, each student proposes to a top-ranked college. Each college chooses the best student among those who proposed. At any subsequent round, each rejected student from the previous round proposes to the top-ranked college that has not rejected him. And each college chooses the best student among those who proposed and matched to it. Okay, and the algorithm terminates when there is no more rejection in a round. The matchings of that round become final. If there is any question on the details of the algorithm, I'm happy to take it now. So, any questions?
Sir, I am Kaibalya. I had a question.
Yeah, please go ahead.
Sir, the college admission problem that we are discussing here now, their preferences are known. Like one individual is filling application, so he has given the preferences. So can we extend this to a specific case of PhD admissions, where individual does not file only one application, rather he applies to all his preferences. So is these canons of matching applicable there? So how can we check for stability? That's the question.
So that's a good question. So I guess let me phrase your question slightly differently. So I guess what you're saying is here I kind of assume. So suppose there is a student and there are 100 colleges. It's kind of not clear that a student would have a well-defined preference ranking over the set of entire 100 colleges. And so it's not clear that if I apply this particular procedure, the student will be able to propose to its top rank and the second rank and so on and so forth, right?
Yes, sir.
So essentially the question is, what if, and probably it's not even practical to have, elicit all the 100 rankings. So what happens if you only take, a truncated, preference of the students and colleges? And so that's a great question, and that's the kind of question that market designers are asking. So suppose there is a behavioral limit on or cognitive limit on the number of colleges I can rank, and the system only allows you to, let's say, submit 5 top colleges or rank 5 top colleges. So what would be the properties of the output of the deferred acceptance algorithm vis-a-vis in an ideal world where each student could rank all the 100 colleges? Okay, so that's the kind of question, people have researched on, and there are papers on that. And so what you would like to say is that in this constrained world where students can submit constrained preferences, what are the properties of the output of the deferred acceptance algorithm? And so these questions have been answered, and I'll be happy to share papers on this topic. But that's exactly, so I'm talking about a very basic and core model, but these are the kinds of extensions people are thinking about. Okay.
Thank you.
Thanks for the question. Okay, so I talked about the version of the deferred acceptance where students are proposing. You can pretty much define an analogous version where colleges are proposing and students are accepting and rejecting proposals. And so it's clear that these procedures will will terminate because everything is finite. The number of students and colleges are finite, and the very fact that if a student is rejected by a college, you cannot go back and propose to that college again. So that basically, so the main theorem of Galen Shapley is that the deferred accepting algorithm produces a stable matching. Both student proposing and college proposing version produces a stable matching. So whatever the preferences of the students and colleges are, you're guaranteed to get a stable matching. Important, student proposing version and college proposing version may produce different stable matchings. Okay. So because I'm a theorist, let me give you one proof. It's just one slide. So the beauty of this paper is that the proofs are very simple to understand, yet very powerful. Okay. So why? So the proof is by contradiction. So what you say is, suppose the deferred accepting algorithm did not produce a stable matching. So that means that there is some college student pair such that C likes S to its match in DA and S likes C to its match in DA. Okay. But students are proposing, so I'm doing the theorem for student proposing version. Because students are proposing and S likes C to whatever it is matched to in DA. Remember how students propose. So they propose to their top ranked colleges, and if they get rejected, they go to the next rank and so on and so forth. The fact that S likes C to its current match means that S must have proposed to C and C must have rejected it, correct? That's from the very definition of how the DA works. Okay. But when does a college reject a student? A college rejects a student only if it gets a better proposal than the student, right? So that's how, again, that's how the DA works. The colleges receive proposals and they choose the best out of that. So which means that if student S was rejected by college C, it must have got a better proposal. And the provisional matching of every college gets better in each round in the student proposing version. So its eventual matching of college C must be better than S, which it rejected earlier. But that contradicts the first part, which says that C likes S to its match in DA. Okay, so that's the contradiction. Okay, so this is a simple proof by contradiction that if there is a college student pair, then it will be inconsistent with the procedure of the DA. Okay, that's essentially the simple proof. But the more interesting part of the paper, Gale-Shapley paper, is that not only is the matching produced by the DA is stable, but it is also optimal in some sense. Okay, here is the sense in which it is optimal. A stable matching mu is student optimal if for every other stable matching mu prime, mu is either strictly preferred to mu prime or mu is equal to mu prime for every student S. So every student prefers mu weakly to mu prime in the sense that it gets a better college in mu than in mu prime, or it gets assigned to the same college. So in that sense, and notice that I'm only comparing mu to another stable matching mu prime. I'm not comparing to an arbitrary matching. So you can also define a college optimal stable matching. And it's simple. If you think for 10 seconds, you'll realize that you can't have multiple student optimal or multiple college optimal stable matching. If a student optimal and college optimal stable matchings exist, they have to be unique. And so here is an example. So if you see, I mean, if you believe me, there are two stable matchings here. One is the blue one and the other is the red one. So here S2 is assigned to C3 in both blue and red. Okay. And so you can see that colleges prefer the red matching because they are matched to better students in the red matching, whereas the students prefer the blue matching. They are matched to better colleges. Okay, so blue matching is not college optimal because there is another stable matching, which is the red matching, which does better than that, and red matching is not student optimal. So what Gale and Shapley showed is that when students propose, the student proposing deferred acceptance algorithm actually produces a student optimal stable matching. So it is the best stable matching for the students. And when colleges propose, it produces a college optimal stable matching. Okay. So if you're in a marriage market If the men propose, they get the men optimal stable matching. And if the women propose, then you get the women optimal stable matching. Okay. And so it's not even clear that a student optimal or a college optimal stable matching exists. But this result actually shows that not only does it exist, but the deferred acceptance, the two-way versions of the deferred acceptance algorithm produces these student optimal and college optimal stable matching. So far I haven't, so there was a question that, the algorithm implicitly assumes that students submit their preferences and colleges submit their preferences. It's not clear that why would students in college be truthful and report their true preferences. Maybe there is a way to manipulate by being strategic and report another preference, even though you like, you're a college, you like student S1 to S2 to S3, you submit another preference of yours, which is not your true preference. Is it possible to manipulate or game the deferred acceptance algorithm? So it's been shown that students cannot manipulate in the student proposing DA, and colleges cannot manipulate in the college proposing DA. I should note that it is possible for colleges to misreport their preferences and be better off in the student proposing DA. And similarly, students can manipulate in the college proposing DA. So you can show theoretically that there is no algorithm that is stable and immune to manipulations from both the sides, both the students and colleges. So this is kind of an impossibility result in this literature. And so far I have talked about this, ideal kind of model where the number of students is the same as number of colleges, and colleges can accept at most one student and so on. Sure. Yeah, go ahead. Is there a question?
No, I don't think so. No.
Okay, thanks.
Yeah.
So it's pretty straightforward to extend this algorithm to allow for larger number of seats in each colleges. So suppose college C has a quota of kappa C number of seats. And so the way you will modify the student proposing deferred acceptance algorithm is that in each round, college C is going to accept all the proposals if the number of students who proposed in that round is less than kappa C. And if you get more than kappa C number of proposals, then you accept the top kappa C proposals and reject everything else. So that's the only modification you need in the student proposing deal. In the college proposing version, in each round, college C proposes to top KC minus the number of students already accepted. Okay. And basically exactly the same arguments will show that both the results that I talked about will continue to hold. So it's not that the results only hold for those special cases, but also for this general case. And for something for you to think about. So suppose I tell you that there's an entrance test and all the students give an entrance test, and basically the score of the entrance test is the ranking of the students. So student 1 got the top rank, student 2, and so on and so forth. And suppose all the colleges have this common preference over students. Okay, so there is no ambiguity about what the college's ranking is, and it is common to all the colleges. So this is something for you to think, that you should try to show that there is a unique stable matching in this case. Okay, and the stable matching can be discovered by the following procedure. Suppose top college of student 1 is C1, top college of student 2 is C2, which is, when I say top college of student 2, it is the top college in the set of all colleges minus C1. And top college of S3 in C minus C1, C2 is C3, and so on and so forth. So basically, you can show that assigning student 1 to college 1, student 2 to college 2, student 3 to college 3, and so on is the unique stable matching. So it's for you to think why it is the case. And essentially, in this case, And only in this case, both student proposing and college proposing produce the same stable matching. Okay, so this is one of those rare instances where you can, non-generic instances, I guess, where both the student optimal and the college optimal stable matching is the same. So I think I'm just on time, so I'll stop here. So there are many resources for you to learn more about it. I think those who are teaching in universities and colleges, I think market design is a great course to offer to undergraduates or even to graduate students. And so these are some of the references. I'm happy to share more references with you if you're interested. So just email me, I'll just conclude by the last slide of the talk, which is basically, now I have talked about two sides of the market and both sides having preferences on the other side. There is another corner of this literature which studies a model where only one side of the market has preferences but the other side does not. So the way to think about this model is one side is agents and the other side is objects. So one side is, let's say, students, and the other side is hostel rooms, let's say, and students have preferences over which hostel room they want to be allocated, but hostel rooms are objects, so they don't have any preferences. Okay, so in this special case where only one side of the market has preferences, there are two more famous algorithms. They're called fixed priority algorithms and top trading cycle algorithms, which also form kind of the cornerstone of this literature. So the Gale-Shapley is for two-sided markets where both sides of the markets have preferences over the other side. Top trading cycle and fixed priority algorithms are for markets where only one side of the market has preferences of the other, and the other side of the market is kind of silent. Okay, so thank you very much. I will be more than happy to take questions.
Thank you so much, Professor Misra. It was just like listening to a great teacher, in fact. So very simple and very clear presentation. And I'm sure there'll be questions from the audience. So we have about close to 10 minutes. So anyone wants to ask a question or wants to clarify something, so please go ahead.
Sir, I had another question. If
Go ahead.
Sir, in this allocation problem, does Pareto efficiency mean allocative efficiency?
Yeah, so Pareto efficiency, first thing, as I said earlier, stability implies Pareto efficiency. So that you can show easily that if you have a stable matching, it will be Pareto efficient. So what do I mean by Pareto efficiency? So I'll say, so let's get to matching. So let's look at this matching. So I'll claim that this matching is Pareto efficient. So what does it mean? That I cannot find another matching where every student and every college is weakly better off. That is, it is assigned to something which is better than its current match, or it is assigned to the same student or college. Okay, so a matching is Pareto efficient if there does not exist another matching where every college and every student is weakly better off. Okay, so you can show that if you have a stable matching, it is also Pareto efficient. So in fact, what I did not discuss is this idea that stability is equivalent to kind of a coalitional efficiency. So coalitional efficiency, the game theory word for that is basically core stability. So a matching is stable if it is in the core of the associated cooperative game. So what does it mean to say that a matching is in the core? So essentially what it says is basically you can take as, so suppose you have a matching like this, and suppose student 1, student 2, college 1 and college 3 who are matched to each other. Basically, they decide to form a coalition. So they, so this is a subset of colleges and students. They say that, look, we are matched with each other, but let's form a new matching amongst us, such that we improve on this existing matching. Okay. So this is kind of stronger than this pairwise idea that I have talked about. Here, I just talked about one pair of college and student getting together and objecting to the matching. But you could talk about, a bunch of colleges and bunch of students getting together and objecting to a matching also. Okay. And
Thank you, sir.
what is surprising is that basically this version of just pairwise blocking is equivalent to a bunch of colleges and a bunch of students getting together and blocking. So pairwise stability, the stability concept that I'm talking about, is equivalent to a coalitional stability concept. And essentially, when this coalition is the entire set of colleges and the entire set of students, we get the definition of Pareto efficiency. So in that sense, the idea of stability is, generalizes the idea of Pareto efficiency quite strongly. So, yeah.
Thank you, sir.
Hello, sir. I have a question.
Yeah, Silu, yeah, go ahead.
So actually, if you see that there are two optimums here, right? One is student friendly, another is college friendly.
Yeah.
So and it is completely free. So they are free to optimize themselves based on their moving strategy. So sir, it might be possible that there might be some constraint. For example, there might be a social planner who wants to constrain that some categories of people has to be like, for example, our reservation system.
Correct.
So they have their own preferences, but
Right,
our
right.
reservation system, brings a constraint so that the social planners' payoff will be. That's the main objective of the social planner.
Right,
So
right.
in that case, how this algorithm will, given the outcome, how the outcome will be.
Yeah.
That's my question, sir.
Great question. So that relates to the third bullet in the slide, which is basically affirmative actions. So how do you modify this algorithm if there is a pre-specified, let's say a mandate to basically allocate, X percentage of the seats to a certain category, Y percentage of seats to another category, and so on and so forth. So how do you modify the deferred acceptance algorithm in those cases? So it turns out the modification is not straightforward. There are many ways to modify it, and basically there has been a recent spurt of papers on this topic, and unfortunately there is no simple answer. But the good news is everything is a modification of deferred acceptance algorithm. So you just need to think how deferred acceptance algorithm does it, and think of the modifications that you need to do for conforming to affirmative actions. Okay. So one way to think, let's say there are two kinds of candidates or for a job. Okay. So there are general candidates and there are reserved candidates, let's say. Okay. So one way to do this is to have two separate allocations for reserved category. So you run DA for reserved and then you run DA for general. The complication is reserved category candidates can also be counted in the general category. So there is an inherent priority amongst the set of categories, right? Because the reserved category candidates can also be counted in the general category. So it's possible to modify the DA and kind of merge these two lists in a clever way, such that the properties that I described, at least some of it goes through. Now, I won't claim that both the theorems will go through, but what you can show is that qualitatively, both the results would kind of go through to such modifications. So I'm happy to share the recent papers. So you will be surprised that, only in 2020, first such papers on these topics have started to come out. So people have started thinking about this. So that's why I said that this is a very relatively new field. And in fact, this paper that I'm talking about, it will be presented, those of you who are interested, I think a version of this paper will be presented in the summer school of Delhi School of Economics by Typhoon Sonmes. So, and they actually take this modification of deferred acceptance algorithm that they propose for affirmative action, and they apply it to Indian context. So they have data for some sectors in Indian job market, and they say that currently the way the quota system is implemented in India is not efficient, and basically the modification that they propose for deferred acceptance algorithm does better than the current system that is being implemented. So I'll strongly encourage you to register for the Delhi School of Economics summer school if you haven't, and listen to this talk. But great question, Silu, great question.
Thank you.
So can I throw in a...
Yeah,
so,
go ahead.
Very nice talk. So a very simple question, and I'm actually not familiar with the literature on this because I don't work on this area much. So what if I have preferences on 2 dimensions?
Great question. Very good question. So, related. So in fact, it goes back to this medical residence matching, where this whole interest in the literature started. So one of the problems Al Roth basically discovered while matching, medical students to internships for hospitals is that often, in fact, a significant proportion of doctors marry each other. And so there are couples. Okay, so basically there'll be a husband and a wife who are both studying medical school, and they have strong preference to be matched together. So if you just type on Google Scholar matching with couples, you'll find a lot of literature on this. And the problem is hard. So essentially what is happening is exactly what Sudipta is saying, that you not only have a preference over the set of medical schools that you want to go to, but there is also this preference to be with your spouse. Okay, so couples want to stay together. Okay, so that's one aspect in which you have preference over multiple dimensions. And the quick answer to Sudipta's question is everything breaks down. So Gale-Shapley's beautiful theorems don't go through anymore. So you don't have a stable matching, and unless the so that is one dimension where you can have multiple multi-dimensional preferences. There is another way in which you can have multi-dimensional preferences. For instance, suppose a college wants to be matched, can be matched to multiple students. So potentially a college could have a ranking over sets of students, right? So that's a very complicated preference. Yeah. So one could ask the question that what kind of college preference over sets of students would still allow this deferred acceptance algorithm to have these nice properties. So there's this whole literature on investigating that particular topic. And the key word for you to look for is substitutable preferences. So if students are somewhat substitutable for colleges, then everything that I have said so far goes through. So the beautiful results of Gale-Shapley still goes through. But if the students are complements, like if student S1 is there and if student S2 comes, then basically S1, S2 is kind of they are complement in the sense that let's say S1, S2 is better than, let's say, S2, S3, or let's say S1, S2 and S2, S3 is there, and S1, S3 is kind of better than both of them, each of them or something. So in some sense, if the preferences of colleges are complements, it's very it's impossible to find stable matching and everything breaks rules. But substitutable preferences, even though the college can admit multiple students, still the results kind of go through. So when I discuss these extensions, I kind of implicitly assume that let me go back to that. So here I kind of assume that preferences of colleges are substitutable. I didn't explicitly say that, but that's what I assume. I hope that answered your question.
Yeah. No, thank you. I mean, thank you. It's a wonderful talk.
No, thank you.
Any more questions or any?
Professor, this is Nivedita. Forgive me for my ignorance. I'm not an economist by profession. I have some background in economics. I'm basically a professor in marketing, academician in marketing. So basically, to start with, whatever I understand of it, the first assumption here is it suits the situation when there is no pricing mechanism. As you said, there is no money transfer to start with. Now, but can we think of a semi situation, say for the state of B school education in India? In that sense, it is also expensive, but there is also a situation when in the second round, there would be students, they would be looking for some sort of merit cum mean scholarship. So there would be a second iteration, which is going to change your preferences in some ways. Semi-pricing mechanism is also introduced. So I guess that would be part of that extension model.
Great question, actually. So so whatever I have talked about will change if we can allow for prices. In fact, good that you brought up the B school example. In fact, I don't know how many of you know that different business schools, even in India, the IIMs, they match students to the elective courses, and these elective courses are basically, they have limited seats, and basically students have to be matched to different elective courses in every semester. And so what they do is, again, there is no money involved in matching students to elective courses, but what they do is essentially they have this idea of a pseudo money. So essentially every student is given some fake monetary amounts, or so points as they call it, and essentially there is a different procedure which is as if the students have money, and they kind of engage in a bidding procedure to figure out what is the best way to match these students to elective courses. So if you look for assigning courses to elective courses to students and bidding procedures, you will find several references to that. So the reason I got Gail and Shapley's pictures now is because when monetary transfers are allowed, there is a separate algorithm which is kind of interesting in its own right. And it was also first proposed by David Gale. So David Gale is really at the cornerstone of this literature. He's the backbone, so to say. So there is a beautiful paper by David Gale with Gabriel Dimanche and Marilla Sotomar. So it's called the Dimanche-Gale Sotomar result in Journal of Political Economy in 1980s. So they propose an ascending price auction. So essentially the idea is very simple. you have a price for each of the courses, let's say, and students bid each on the courses and outbid each other till there is no demand for a particular course. And so it's kind of a intuitive bidding procedure. If I had time, I could have discussed it. And they show that surprisingly, with prices and monetary transfers, that procedure has exactly the same properties that I discussed today of the deferred acceptance algorithm. So they show that there is a set of stable, quote unquote, stable matchings in that model with monetary transfers, where students could have preferences over prices and college pairs, essentially. And there is also a student optimal stable matching. There's also a college optimal stable matching. And there are two versions of this auction procedure, and one version terminates with a student optimal one, the other version terminates with a college optimal one. So there is a parallel universe with prices and transfers. And what is surprising is that there are algorithms in that universe also which exhibit similar properties. Okay, so it's excellent that you asked this question, because market design is concerned with that literature also.
Yes, so it's also partly, I mean, I don't understand much of the maths, but yes, thinking intuitively from my practical experience, for example, in the reserved category, someone who gets an offer from both Ahmedabad and Calcutta, but because Calcutta, say,
offers scholarships.
And maybe less, my 5 lakhs or less than, but there is someone from the reserved category who can afford A, but so that happens. So I've seen people doing. So that I'm just thinking that semi-pricing mechanism could be introduced.
Right. Right. So I mean, the specific model that or the application that you're thinking would have some details that would not be directly fitting into what I'm talking about. So that, in that sense, what Alroth said was you need to get into the engineering mode and basically, come up with your own model for the particular application that you have in mind, and try to tweak this particular algorithm in some sense. But what I have discussed is basically the core of the of the literature.
Right. Thank you, sir. Thank you so much.
Yeah.
Any more questions or Professor Misra? If I mean, we have almost exhausted the time, but then I had just as I said, I just listened to your this thing with great interest. But I have a little. It's not exactly a question, but I'm sort of like, I have a little concern that are we sort of talking generally about, let's say, systems where markets operate perfectly. Meaning that I'm sort of bringing in two elements. One is what I may call as, whichever way, like if there is an introduction of information asymmetry, or particularly because we are talking about talking at a time when information availability or access to information can actually very deeply influence my choice. So that is number one. And the second thing is, so what happens if there is the playing of a vested interest? So are they like, these are two disturbing or two, let's say, external factors which might completely mess up the process of choice, ranking, and in the end, matching.
Right, right.
Yeah.
So that's a great question, actually. So this slide, partially addresses that in the sense that as you said, I mean, students or colleges can game the system, and why should we assume that we know the preferences of students in colleges? And so there should be there should be basically mechanisms to elicit preferences, and students and colleges should have incentives to report this preferences. And so at least what we can say is that the deferred acceptance algorithm is whichever side proposes has no such incentive to do so. Unfortunately, it's not it's not strategically stable from both sides of the market, and so there's been a lot of research about what to do with that. So people are thinking about that, and so all this is kind of the second other point that you mentioned is like sometimes students or colleges may not have information about their preferences, and there might be some outside expert or social planner which can provide incentives to acquire this information. So information acquisition and basically discovering your preferences. And so for instance, students may not know the particular details of colleges, and a social planner can disclose this information and what is the optimal amount of information to disclose. And so these are basically very recent topics of research. So it falls into this literature on information design and mechanism design. It's a marriage of market design and information design. So it's very much a hot area of research these days. In fact, one of our own students, who is a PhD student in University of Chicago, Sulagna Dasgupta, has a beautiful paper on this topic, and so it's very relevant. So unfortunately I cannot answer in any detail the question to it, but all I can say is it's particularly pertinent and relevant in today's day and age. Yeah.
Thank you, Professor Misra. If there is any, this is the last call for any questions. Anyone still wants to ask something very briefly? If no, then let's join together and thank Professor Debasis Misra for this great presentation. And we're particularly thankful to him because he also introduced to many of us a kind of a new challenging topic. And as the discussions showed and the way he explained, looks like there is much ground to cover, and maybe the younger generation would benefit a lot from this presentation. So thank you, Professor Misra, very much to have spoken to us. It's extremely kind and nice of you. And it's also very befitting also to have spoken in this particular event where we are celebrating the scholarship of Professor Baidyanath Misra. So many thanks on behalf of the Odisha Economic Association. And I thank Professor S.N. Tripathi, the President of the Odisha Economics Association, for being there all through, for having guided us and sort of given the introductory remarks. So many thanks, Professor Tripathi. And let me also thank both Dr. Basant Misra and Professor Sukant Misra to have joined on behalf of Professor Baidyanath Misra's family. It was very nice of them. I should also thank Mr. Lakshmikant Goal, who is a doctoral student at Niger, Bhubaneswar, but then he was behind organizing the technical part of it. So he managed the platform. Many thanks to the young scholar and many who joined. And last but not the least, Dr. Amarendra Das, who has been very, very dynamic, active, and so a lot of energy has been put by him. He's the one who informs everyone, he coordinates, and so it is his effort in a major way that makes these events successful. So with that, unless Professor S.N. Tripathi sir, if you want to say some few things towards the end, with that we can end.
On this memorial occasion of 101th anniversary of late Professor Baidyanath Misra, the memorial lecture has been delivered by Professor Debasis Misra. I express my thanks and gratitude to Professor Debasis Misra, Professor, Indian Statistical Institute, Delhi, for his extremely insightful talk pertaining to market designs and matching and its applications so lucidly and so elaborately. I am really thankful to him. To Professor uh, Sukant Misra and Dr. Bhashant Kumar Misra, I express thanks and appreciate for their presence in this memorable event. Throughout the occasion, they were present, and so I am very much delighted. To Professor Keshav Das, Gujarat Institute of Development Research, I express thanks for moderating the event. In fact, I express my thanks to all of you for your keen interest and cooperation and for being with us throughout this lecture. So with this, I think the event is closed. I express thanks to all and namaste to all.
Thank you very much.
Thank you very much.
Thank you for
Thank you.
attending. Bye.